For Chapter 10, we're going to be doing hypothesis testing and confidence interval construction for two populations. In this chapter, we'll be able to go over how you find the difference between two population means and two population proportions. For example, suppose the claim was that the mean final grade for on-ground statistics students is higher than the mean final grade for online statistics students. In that example, we'd be testing the means, the difference between the two means. Another example would be to test the claim that the percentage of left-handed female students is different than the percentage of left-handed male students. In that example, we would be testing the difference between the proportions. Let's start off testing the two population means, where we compare the final grades of on-ground statistics students to online statistics students. So let's go ahead and test two population means. We'll test the claim that the mean final grade for on-ground statistics students is higher than the mean grade for online statistics students. We'll use a 0.05 significance level. So to do this, let's first identify the two populations that we're comparing. The first population will be our on-ground statistics students, and the second population will be our online statistics students. From each of those populations, I need to select a random sample. Suppose that I select a random sample of on-ground statistics students of size 50. Of those 50 students, if I calculate their average final grade, their mean final grade, the sample mean grade comes out to be 78.4. So I use data to calculate that. And the sample standard deviation comes out to be 20.3. So I'm going to go ahead and put a subscript of a 1 on n, x bar, and s to indicate that this is the sample for population 1. These are the sample statistics for the first population. I'm going to want to calculate those same statistics for my second population. So let's say I collected a random sample of size 85 from my online students, and I found their sample mean grade, so x bar sub 2, to be 74.5, and their sample standard deviation to be 25.1. And again, I'm putting a subscript of a 2 on each of these statistics to indicate that they are coming from the second population. Now our job is to go ahead and decide what are our hypotheses. So let's look at our claim. We're saying that the mean, so we're testing the mean grade for on-ground students is higher than for online students. So our claim in symbolic form says that mu1, the mean grade for on-ground students, is more than mu2, the average grade for online students. So looking at our claim in symbolic form, we do not see any equality symbols. So that means that our claim corresponds to the alternative hypothesis. Mu1 is greater than mu2. Our null hypothesis then will look like mu1 is less than or equal to mu2. And so again, it's not a bad idea here to go ahead and write what each of these claims represent in words. So in words, the mean grade on ground is more than the mean grade online. So that is my alternative hypothesis. And then the null hypothesis contradicts that by saying the mean grade on ground is not more than the mean grade for online students. The other thing I want to point out about these hypotheses is they can actually be written in symbolic form another way. So let's again look at the alternative here. If we're saying that mu1 is greater than mu2, if we moved this mu2 over to the other side, in other words, we subtracted mu2 from both sides, you'd have mu1 minus mu2, and what would be left on the other side of the inequality symbol is 0. So this is another way of writing the hypotheses in symbolic form. Similarly, we can write the null hypothesis as a subtraction statement as well, we're saying that mu1 minus mu2 is less than or equal to 0. Or in other words, mu1 minus mu2 here is less than 0. So the difference in the grades is negative. And this statement is saying that the difference in my on-ground students and my online students' grade is positive, which means that mu1 must be greater than mu2, which is exactly what we started our statement with. So now that we have our hypotheses, it's time to calculate our test statistic. And so the way that we do that is realizing that we have a sample standard deviation and not a population standard deviation, means that our test statistic is going to be a t-score. So the formula for finding this t-score is to take the difference in the sample means, so x bar 1 minus x bar 2, minus the difference in the population means, mu1 minus mu2, so the claimed values there, all divided by the square root of the sample standard deviation squared for sample 1 divided by its sample size, plus the sample standard deviation from population 2 squared divided by its sample size. So one thing I want to point out in this test statistic is you have x bar 1, you have x bar 2, you have s1, you have s2, you have n1, you have n2. But do you have the claimed value? Nowhere in this problem does it say, I claim the grade is, like what we did in chapter 9. It's only comparing the two. So more often than not, if you're just comparing the two populations, the difference between mu1 and mu2 is going to be 0, right? And we can actually see that right here in both of these claims when we write them as a difference. That's actually why this section is called testing the difference in population means or population proportions, because we're just comparing how they relate to one another. And so when we subtract them, we end up with 0. Now, this formula is pretty cumbersome, but it's easy for us to plug those numbers in and just, again, realize that this whole statement, right, this piece right here is 0. But Statistic is going to calculate this number for us. And when I plug this into Statistic, I end up with 0.9857. So my test stat is 0.9857. So with that test stat, the next thing that I want to do is calculate my p-value. And so again, I'm using the student t-distribution here. The degrees of freedom are going to be whichever is smaller between sample size 1 and sample size 2. So the degrees of freedom are going to be n1 minus 1, so they would be 49 degrees of freedom. So our normal distribution, our t-distribution with 49 degrees of freedom, a test stat of 0.9 is maybe about right there, 0.99. And this is going to be a right-tailed test because my alternative hypothesis has the greater than symbol there. And so this p-value, this area that I just colored in right here, is 0.1631. So now we compare that p-value to our significance level of 0.05. Our p-value is greater than 0.05. So what conclusion do we make? Do we reject or do we fail to reject the null hypothesis? So that's right. Since the p-value is 0.1631, it is greater than the significance level. That means we fail to reject the null hypothesis. So how do we use Statistic to get these values a little bit quicker? So you're going to go to Analysis, you're going to go to Hypothesis Testing, and then you're going to look for the two-sample hypothesis test with independent means. So here's a screenshot of what this problem looks like in Statistic. So we can see here that, first of all, I've changed my alternative hypothesis to represent that mu1 is greater than mu2, population 1 on-ground students, is greater than population 2 online students. I have my 0.05 significance level. You can use the data if you want to, but I didn't give you data in this problem. I only gave you the statistics. So that was my first sample was size 50 with a sample mean of 78.4 and a standard deviation of 20.3. My second sample was 85 with a sample mean of 74.5 and a sample standard deviation of 25.1. We get our test statistic here, so 0.9857, and then you can see our p-value of 0.1631. So that's the information we used to come to our conclusion. Now it's time for the interpretation, the wordy interpretation of that conclusion. So what does it mean to fail to reject the null hypothesis in this case? Remember what our hypotheses were. Let's just get those written up again. We said that mu1 was greater than mu2. That one was our claim, that the mean grade of on-ground students is higher than online students. So the null hypothesis is that it is not greater, that it is either equal to or less than that of online students. So by failing to reject the null hypothesis, we are not rejecting this statement, which means if we don't reject this statement, we can't support the alternative. So there is insufficient evidence to support the claim that the mean final grade of on-ground students is more than the mean final grade of online stat students. So here's a recap of all the components that went into this hypothesis test for the difference in the means. So first of all, our notation, our sample size is N1 and N2 from both populations. We go ahead and calculate the sample mean, x bar 1 and x bar 2 from both populations, and the sample standard deviation, s sub 1 and s sub 2 from both populations. It is possible that you could be given the population standard deviations for each of those. So in that case, you would be given sigma sub 1 and sigma sub 2. But it's most likely that you would only have these sample standard deviations. Our hypotheses, we have three different types of tests, right? A two-tailed test, a left and a right-tailed test. In a two-tailed test, that means that we're saying that mu1 does not equal mu2. So our null hypothesis would say that mu1 equals mu2. Now again, remember that there is another way of writing this. We can write it as the difference because it's the difference that we're taking in order to calculate the test statistic. That's really what we're testing here, is the difference in these values. So if mu1 does not equal mu2, then mu1 minus mu2 is not equal to 0. In a right-tailed test, we would be claiming that mu1 is greater than mu2. So that means our null hypothesis would be mu1 is less than or equal to mu2. And again, you can think of this as the difference. So if mu1 is greater than mu2, then the difference of mu1 and mu2 is going to be greater than 0. It's going to be positive. In other words, the first mean, mu1, is bigger than mu2. And in a left-tailed test, we would be saying that mu1 is less than mu2. So that's like saying statistics students on ground score worse than online statistics students. So as a difference, that would say that mu1 minus mu2 is less than 0 or negative. And then the null hypothesis here would be that mu1 minus mu2 is not less than 0. So mu1 is greater than or equal to mu2. So those are the three potential types of hypotheses we could have when testing two population means. Our test statistic is calculated using this formula. So it's the difference in the sample means minus the difference in the population means, which again, remember that this right here, this is usually 0. Unless the problem says otherwise, you can assume that that number is 0. Our test statistic is going to be a t-score, just like we learned in chapter 8 and 9, if we only know the sample standard deviations. Otherwise, it's going to be a z-score if we have the population standard deviations. So primarily, you're going to be using this formula if sigma is unknown. But if sigma is known, then you'll use the z-score formula. Our conclusion that we make is going to be no different than what we did in Chapter 9. We're going to be using the p-value method. So if the p-value is less than your significance level alpha, the conclusion is still going to be to reject the null hypothesis. But if your p-value is greater than or equal to alpha, you're going to fail to reject the null hypothesis. Now, when you're using a t-distribution for your test statistic, the degrees of freedom here are going to be whatever is smaller between n1 minus 1 and n2 minus 1. So in our example, n1 minus 1 was smaller because I took a smaller sample from my on-ground students than my online students. So the last thing that we need to discuss is how do you construct a confidence interval for this difference? So let's go ahead and look at that. So I'm not going to go through how we do this by hand because we'll just use Statistic to construct these confidence intervals. But remember, what we're testing or what we're estimating with the confidence interval is the difference in between the two means. So that means that our point estimate becomes this difference between mu1 and mu2. So our point estimate is the difference of the sample means. So that's what's in the middle of our confidence interval, is x bar 1 minus x bar 2. And so then in order to get that upper limit, you take that x bar 1 minus x bar 2 and you add the margin of error. That's going to be your upper limit of the interval. And then to get your lower limit of the interval, you take again that point estimate, which is the difference in the sample means, and you subtract the margin of error. And that's what's going to get your lower limit. And again, this is what we're trying to estimate, is the difference between mu1 and mu2. So in Statistic, you're going to go to Analysis, Confidence Intervals, and then you're going to go to Mean 2 independent samples and input your data. So here's a screenshot of what that looks like. So I went ahead and put into Statistic the data from our problem where we were testing the difference between our on-ground and our online statistics students. So same sample, of size 50 here for from our first population with the same sample mean and standard deviation. And then our second population, which was my online students, and our sample mean and our sample standard deviation. So here's our confidence interval. So I chose to make a 95% confidence interval. The confidence interval goes between negative 3.93 and positive 11.73. So it's interesting to talk about the different interpretations that we can come to for this confidence interval. Obviously, we can state our first and most generic interpretation, which is that we are 95% confident that the difference in the population means is between negative 3.93 and 11.73 points. But besides that generic interpretation of saying we are 95% confident that the difference between the mean on-ground stats final grade and the mean online stats final grade is between negative 3.93 and 11.73, we could also talk about what numbers this interval contains. So notice that it starts at a negative and it ends at a positive. That means somewhere in between these two numbers is 0. And what does it mean if mu1 minus mu2 is equal to 0? Think about it like this. If mu1 minus mu2 could possibly be 0, then what do you know is that mu1 could equal mu2. And so that's what this statement says right here. Since 0 is in the confidence interval estimate of the difference between the means, it is possible that the mean on-ground stats grade is equal to the mean online stats grade. So this is a more powerful conclusion than this sort of generic conclusion that we've been using in Chapter 9. Both of them are great to write, and in fact, I would expect that you know how to write both of them, but I think that the second conclusion is a little bit more interesting. We can even take it a step further, and this is why you can see how confidence intervals also help promote hypothesis testing, because by saying that 0's in this interval, then we know it's possible that these two values, mu1 is equal to mu2, rather than assuming that mu1 is definitely greater than mu2. But what numbers does this interval primarily contain? So it goes from negative 3.93 to positive 11.73. this interval has more positive numbers than negative numbers. What does that mean about the relationship between mu1 and mu2 if we have more positive numbers than negative numbers? Since the interval contains more positive numbers than negative numbers, it is likely that the mean on-ground final stats grade is higher than the mean online grade. Did we actually prove this? No, but that's what this interval suggests by having more positive numbers than negative numbers. That means that mu1 minus mu2 is most of the time positive, and if that's true, then mu1 is greater than mu2.